Alright, so let's step through this second notebook, in which we'll be implementing and training a fully connected network with a single hidden layer to classify MNIST digits. So you can kind of think of this as the hello world task of PyTorch. And so this will serve to illustrate what the best practices are for constructing a typical deep learning pipeline in PyTorch. Right, so let's jump right in. Let's look at this first block where we're just doing our imports. So yeah, I've just included NumPy and matplotlib here because we'll be plotting some stuff later. These are various PyTorch related imports. So NN, the torch.nn library is the set of neural network utilities, and functional is a set of functions that, let's say, we have stuff like loss functions here and activation functions, which is sometimes convention to use the nn.functional package to import them. We've got torch.optim, which are our optimization utilities. We've got our data set and batching utilities here, which we'll be seeing. And finally, we've got Torch Vision, which is a set of computer vision related utilities. So we're interested in MNIST. In this example, we'll be using datasets package to easily import the MNIST dataset and some transforms to perform some basic pre-processing on our MNIST digits. So just as before here, we're setting the manual seed and we're setting our device to a CUDA device, in this case a GPU, because we have a GPU on this machine. So I just printed out here to indicate we're using the GPU. And so just stepping back here, what are the steps of the pipeline, right? And to define our model, we want to iterate then through fetching batches of training data, by feeding them into our model, building predictions for which we can compute a loss. In turn, we'll compute the gradient of that loss with respect to our model's parameters. And finally, we update the parameters using that gradient in some gradient-based optimization method. And then we repeat, right? We reset whatever gradients we've logged and we repeat. We obtain the new gradients and update and so on. So let's see how we will do this. Let's look at the first step, defining the model, right? So in this example, we're interested in constructing a one hidden layer fully connected network, right? So we're going to go from the input to a hidden layer and then straight to the output predictions. And so just about every case where you want to define some kind of model or some kind of subunit of a model, the way we do it in PyTorch is to define a class that inherits from nn.module, right? And so this behind the scenes does all sorts of repetitive, tedious work, and it kind of hides a lot of repetitive, tedious work from us, right? So when we define something that inherits from nn.module, all we need to do is, in the constructor, typically we define what are the building blocks we're using and anything with learnable parameters. In addition to various other things we might want to log about our model. And then all that's left as a minimum to define is the forward method, which tells us, how do we do a forward pass through the model? How do we feed in an input to compute the output? So let's look for this specific model and what we're doing in the constructor. So first of all, of course, we're calling the constructor of the superclass, right? And next, because we're defining a fully connected network, we're assuming we're going from some input of size 784, and we'll see why this is the case for MNIST soon, to some hidden layer of size n hidden. And note we're passing n hidden as an argument of the class, and we're asking for we want a bias, right? So this nn.linear is performing an affine transformation on the input. So we're going to pre-multiply by some weight matrix, and because we passed bias equals true, we're also going to add some bias vector. And so that's just the first block here. And finally we need to, again map that vector of hidden units to a vector of predictions. In this case 10 predictions, because we have 10 digits for MNIST. And similarly this is going to be an affine transformation, and we're going to request that it does use a bias, right? And so these will note that these two building blocks, this nn.linear class is also this, I think an nn.module, something that inherits from nn.module. And so under the hood, what's going on here when you create an instance of this class, all the learnable parameters in the components defined in your constructor are going to be grouped together in a way that makes them all easy to access at once, right? So as we'll see later, typically we want to very easily, given the model, just query for all their parameters, because we want to update those parameters typically by computing their gradients at some point. All right, so but all that is abstracted away from us, and in PyTorch, thankfully, all of that is done behind the scenes, and as we'll see later, it's really simple to query for the parameters of this model when we define things in this way. So after we've defined what the components of the model are in the constructor, the forward method would define what computation is performed on the model, on the inputs when fed into the model. And so over here we'll see the first step. First of all, as we'll see, the inputs here, we're going to be considering a batch of MNIST digits, right? So let me just clarify down here, written down something to clarify what the input is actually going to look like in this example. So the MNIST digits, as we'll see, they're going to be coming in the form, a single image is going to come in the form of a tensor of shape 1 by 28 by 28. So this is just, we have one channel here because they're going to be monochrome images. And let's consider straight away that we're feeding in a batch of such images to our model, right? So we have this additional batch dimension, and the convention in PyTorch is that the batch dimension is the leading dimension, and so we have this value b indicating how many observations we have in the batch. So as we saw in the constructor, the linear building block performs an affine transformation on some vector, right? In this case, it also works on a batch of vectors. But what we have here, we have a batch of these tensors, right, of shape 1 by 28 by 28. And what this first bit is doing here, we call inputs.view. This -1 is saying, no, leave the first dimension, which in this case corresponds to the batch dimension, untouched, and then collapse all the remaining dimensions into one of size 784, right? And the 784 comes from multiplying these three values. So this is just because we need to flatten. This is expecting a vector or a batch of vectors, right? We need to flatten it into something that is compatible with what it's expecting. So once we've done that, this is essentially going to map to some set of hidden units, or rather, after the next line where we've applied some activation function, in this case a rectified linear unit, this h is going to denote the set of hidden units for the given batch of inputs. And finally we're going to pass h once again into the second affine transformation to get our output. And we'll note, this is a multi-class classification problem, so we need to softmax our output. And notice here I'm using a log softmax, and I'm very clearly specifying the dimension over which the softmax needs to be applied, right? Which is in this case going to be the trailing dimension. And the first one is going to be the batch dimension. And I use log softmax because of the to play nice with the loss function I'll be using later, but there are different ways of doing this, right? Typically we use, it's advisable to use things like log softmax to avoid, well, if you use log softmax in conjunction with a specific loss function, as we'll see, just ensures that we're not performing any needless numerically unstable operations. Right, but just to summarize, very simple here. This is how we define a basic model. Constructor, define components of the model with the parameters. Forward method, we define how the forward pass is performed given whatever arguments we pass as input to the model, right? Very simple. Now moving on, let's look at, I've defined this utility function here to capture what we want to achieve in a single epoch of training, right? What do I mean by a single epoch? I mean we want to fetch batches of some data set, and we want to essentially get predictions, compute losses, get gradients, and update parameters for all of those batches, right? Once we've exhausted all the data in the data set, by stepping through all the batches, we say that's one epoch of training, right? And so I'll come back to this utility function, which looks quite long, but it's mainly just documentation. It's there for your reference, right? It's actually extremely concise. So all the operations that we need to write out to carry out what I described, they're very, very, very concise, as we'll see. So I'll return to this function shortly. Let me just let's show you where it fits into the big picture, right? Oh, and just below I have this additional utility function for evaluating the model, right? So it takes the model as an argument and some test loader, which we'll see this is what we use to iterate over batches of, in this case, the idea is for some test set, and it's going to give us the accuracy of the model that we've passed in on the test set. And I'll step through this later. First though, let's look at some of the components we're going to need to feed in as arguments to both of these methods. So as a first step, how do we define our data set? So we're interested in MNIST here. And how do we, in some easy way, fetch batches from this data set? And so this is what we're capturing over here. And there's further information in the PyTorch documentation if you'd like to consult it. So in this first block of code, let's see what's going on. So it's just printing out some, because we download. I'll come back to that in a bit. Let's just step by this through this bit by bit. So starting over here, so as I mentioned, we're interested in working with MNIST in this example. And recall we've imported this datasets package from Torch Vision. It gives us this utility for downloading and creating MNIST, an MNIST dataset, right? First argument is just telling us where to download the stuff, because we said download equals true if we don't have it stored already. The train flag is indicating that this object, it's going to denote the training set. In both the cases of the training and the test set, we're passing in this transform, which we've defined here, which is a series of pre-processing operations we're applying to the data that this class is going to be representing. So the first step, again, this is something we've imported from Torch Vision. First step, we're going to coerce, or rather switch something from, in this case, an image object to a PyTorch tensor. And secondly, we're going to normalize this tensor, right? So what this normalize function does, so this is the values for each channel by which we're going to normalize the mean, and this is how we're not going to normalize the standard deviation. And because we have only one channel for these MNIST images, we just have a tuple of length 1 in each case. So this is going to be subtracted from the images, right? And there's going to be the images are going to be divided by this value to give us 0 mean and unit standard deviation. Right, so this covers this first bit. And so given the data set, we can query for observations in the data set using the square brackets. It's going to give us observation at index 0. It's going to return an image and the target for that image, right? And at the bottom here, we're just printing out what that is, right? So 5 the target, size of the image, 1 by 28 by 28 as I mentioned, and just above here we're using matplotlib to plot that image, right? We see it's clearly a digit of a 5. So that's how we define the dataset objects in PyTorch, and you can consult the data utilities documentation in PyTorch to look up some other ways of constructing datasets. Let's say you might be interested in working with some images stored on disk, for instance. You want to retrieve images from some nested folder structure, for instance. So PyTorch provides all sorts of utilities for helping with that. But what about getting batches of data from your dataset? And this is what this block of code is doing. What in particular the data loader class is helping us with. So the data loader is essentially this iterable object which is going to yield batches of data from whatever we pass as whatever data set we pass as the first argument. Right, it says training data, here's MNIST 60,000 items. You can specify a batch size that we'd like, and very important in most cases, you want to shuffle your training data before pulling out the batches, right? Otherwise you might run into all sorts of trouble, problematic gradient information arising from any structure that might be present in the specific default ordering of the training data. So you typically always want to pass in shuffle equals true, right, for your training data set. And yeah, same thing for the test data set. Get this test loader, not really important to shuffle in this case, and we use a larger batch size, and don't really need to, but kind of works with this example. And so I mentioned both of these things are iterable things. So let's create an iterator and yield some item from it. It's going to yield this tuple of a batch of inputs and a batch of targets, right? And if we print, first of all, what the shape of the inputs is, first of all, exactly as we expected here, we have a batch size, right? And then the shape of the image. Same for the targets here. The targets are just going to be these integers, right? Because we have a batch size of 64, it's just going to be a flat vector of length 64. And just below we printed out what these two things look like. The first case is the batch of images, which is not really that informative, I guess, to look at. We'll note, you might see why this minus 0.4242 appears everywhere. Well, it would have been 0 if we hadn't done our normalization, but the normalization step when we constructed our data sets is what's giving us here this value repeated everywhere. And if we scroll down and we see, so this is going to be the batch of labels, the targets, right? 64, so length 64, and they're just integers denoting the corresponding digits in the batch. So again, very simple. We want to iterate over the data set in batches. You'll just iterate over these train loaders, and they will feed out to you batches of the inputs and corresponding targets. And we'll revisit this when we go back up to look at how we've written the training utility method. And so before doing that, let's see how this all fits into the big picture of this example. So this is the code we're going to run. We're going to call to run everything. So we construct our model here, an instance of our model with 32 hidden units. And so this coming back to what I mentioned about indicating to PyTorch that we want to run things, in this case on the GPU. So at the top, you'll recall we set that device variable, right, which indicates we want to work with the GPU. And to indicate to PyTorch that we want the model to reside on the GPU, and any computations it's involved in should take place on the GPU if possible, we call .to and pass in the device. Right, simple. So we also need an optimizer, right, to give us some gradient-based optimization method. And again, these are very simple to define. As a first argument, we always pass in whatever parameters we'd like to compute gradients with respect to. And so this is what I was referring to earlier about how easy using nn.module makes this, right? As long as we've defined our model with nn.module and we've done everything correctly, and it will make it easy for the library to track any learnable parameters. What we have to call here is we take our model and we call its .parameters method, and that's going to return an iterable of all the trainable parameters in the model that the optimizer needs to keep track of and update once we've computed the gradients, right? And then following that, we typically have a number of optimizer specific arguments. So in most cases we always have a learning rate, right? And for SGD we could also set a momentum parameter, right, which I'll encourage you'll probably be finding out more about this as you progress through the course. But I just wanted to illustrate how you set how you use SGD with momentum in this example. And so now if we looked up what we defined in those utility functions, we have everything we need to run things, right? We have our model, we have our training loader, we have our optimizer. Epoch is just what epoch we're on currently, it's just for cosmetic reasons. Same thing for the test utility function, right? So we're going to train for one epoch, test to see what accuracy we hit, and we're going to repeat for 3 epochs. And finally, this last bit here, before I go up to the main important part of this notebook, which is these functions. This is how we'd go about saving the weights, let's say, of the model, right? So again, very easy. We call the state_dict method of some object inheriting from nn.module. It's just going to return all of the any of the information that we need to restore the model to its current state, right? And we can call this torch.save utility method to save it to a file with this name. If we want to load it back, it's called model.load state_dict, pass in as argument torch.load with the corresponding file we saved to. Right? All very simple, all very important to keep in mind. When you spent all this time training your model, and you just want to make sure that you're periodically saving your parameters at checkpoints. Let's say, just in case your session crashes or something like that, you can very easily restore things to the state you were in when it crashed in this way. And another thing I'll mention right now, so it's not really relevant in this simple example, you will also need to do this for certain optimizers, right? So certain optimizers are stateful, and you will need to also save and restore the state of the optimizer for some other optimizers you'll be coming across if you want to, let's say, pause a session and resume, or just start again from some checkpoint if, let's say, your session collapsed, right? So just keep that in the back of your head, and just remember that you might to check whether your optimizer is stateful and needs to also be accounted for when you're trying to restore from some checkpoint. And so finally, let's go back up and look at how we've written these two methods. So first, the train method. So as I mentioned, this is just going to perform one epoch of training, and this is going to involve iterating over batches of the data, and for each batch we're going to obtain predictions, compute a loss from those predictions, compute a gradient of that loss with respect to our parameters and we're going to update our parameters using that gradient, and we're just going to repeat, right? So let's see how we do this. As the first step here, we'll notice that we have this loop here, right? So we're iterating over train load there. So these are the input images in our case, and the labels. I've also added this enumerate thing here just for cosmetic reasons. It's not essential, right? But it's going to tell us how many batches we've done just for logging purposes later, right? You guys will see. It's not that important though. The important thing here is that when we iterate, we're going to be given a batch of inputs and a batch of targets. So the first step, we want to indicate to PyTorch that we want this data to reside on the whatever device we've set device to be equal to. So in this case, the GPU. So this is important. It's not going to run if you have your data on, set to, by default, it's going to be try and run things on the CPU. If your model's on the GPU, it's just going to throw an error. Next, we have this step of zeroing the gradients. So this is important to do. So when you call optimizer.0grad, you'll recall when we constructed the optimizer, we passed in some set of parameters we'd like to keep track of. What it's going to do when we call this is it's going to access the grad attribute of any of those parameters, and it's going to nullify it. Basically, it's going to delete anything that we've stored there and set to 0. And so this is important because if we didn't do this, the AutoGrad engine is going to continue logging any operations we do involving that, those learnable parameters, and the gradients are going to accumulate, right? So there are cases where this gradient accumulation is useful. Let's say, I'm not sure how relevant this will be in this course, but suppose we're working with a model and data that's too big to fit in memory with the batch size we're interested in working with. One way of getting around that is to split that large batch into smaller sub batches, right? And so you pass, you get predictions and compute gradients with respect to the first sub batch. You don't set the 0 grad to retain the gradients, and pass in a new sub batch and compute a new gradient. And because you've not reset the gradients, the new gradients you've computed are just going to accumulate, right, in the grad attributes. And once you've exhausted all these sub batches, in effect what you're going to have done is you're going to get the gradient as you would have obtained had you done the forward pass all at once through the entire batch, right? So this is just something to keep in mind. When might we not want to use this? Just keep that in mind. I doubt you'll run into this situation in this course. You're not necessarily working with enormous models, right? But this is one trick which you might want to look into going forward, should you ever encounter a situation where you don't have enough memory to work with the model or batch size that you're interested in. Right, so always typically, though, in this course we're going to be interested in zeroing the gradients before doing any computation and calling any backward methods. The next step, so this is computing model predictions from the inputs. So nn.module instances, they're callable, and calling it is just going to call the forward method on this argument, given these arguments. And so these are going to give us our log softmax outputs. And then we're going to take these outputs to compute our loss function. So NNL loss, it's designed to accept the outputs of a log softmax, right? It's going to give us the negative log likelihood loss. So all this is equivalent to essentially computing the cross entropy loss with this multi-class classification question problem. So we're also passing in the targets, which are going to be integers. And so be very careful. Sometimes certain loss functions expect, let's say, the targets to be integers and others don't. So just keep that in mind. You may just encounter certain errors sometimes when passing in the wrong data types here. And finally, as we saw in the previous notebook, compute the gradients of the loss with respect to any parameters of the model we just call loss.backwards. And the autograd engine is just going to do the backward pass, essentially. It's going to step back through the computation graph we've called so far, and it's going to log any gradients as defined by the computation graph. And so that's going to set the gradients in the grad attributes of any tensors with requires grad equals true under the hood. The final step then, we instruct the optimizer to update the parameters on the basis of those gradients using whatever rule the optimizer defines. In this case, we're using SGD with momentum. And I've included some basic here logging information with every so many batches, for whatever we set the log interval to. In this case, 100 by default. It's going to print some logging information. Right? It's going to print the epoch, the batch, and it's going to print the current loss. And so this is another important thing. So you should call the loss.item method, the .item method of a tensor if you want to just log something. So this is going to return some Python object as opposed to some torch.tensor. So this is usually best practice, because we have to be very careful with working around the autograd engine sometimes. So autograd is always paying attention to any computations we perform on any nodes in the computation graph that involve tensors we've indicated we want gradients with respect to. So unless you explicitly want to manipulate something in a way that is going to affect your gradients, if you're just logging something, just query for this item method, which is going to give you some Python number, in this case some floating point number that is completely unrelated to the computation graph. So yeah, make sure you use this if you want to log something. Just always be aware of how the autograd engine works and work around it. And so that's all the train method does, right? I'm just going to iterate through the entire data set once. That's what the train loader is going to run out, stop yielding once we've used up all the batches, and then we'll just return, right? And so the test method has some important differences. The main difference is that when we're testing the model, we're not interested in computing any gradients, right? And computing gradients is quite expensive relatively, right? So we need to log in the forward pass a lot of information, which it costs memory and other resources. And we have this utility in PyTorch to indicate to the autograd engine that we're not interested in, when we're not interested in computing gradients, we just use this with torch.nograd context, and any computation taking part in that context is essentially taking place with the autograd engine switched off. And so it's not going to log any of the information we need to compute gradients. But similar to before, what this function, we're just interested in computing the accuracy and the loss, the average loss on some test data sets. So we're feeding in the model and some test data loader. And so again, we're iterating over the test loader here. We're sending to the device, getting predictions, and this last bit here, we're just computing the loss. And so this is some code which you can look at in your own time. The argmax here is just taking the largest value in the output predictions as what we might consider the prediction that the model is currently edging towards as the right answer for this given input, and we're comparing it here to the ground truth and adding to our tally of how many we've gotten correct so far. And we're printing Here's the accuracy here, how many correct we have so far, all over the total number of observations. And so that's all this is doing. Right? And so yeah, let's just step through things bit by bit. And just before we end here, we'll run the training loop at the bottom, just to see what's logged, just to wrap things up. Right, and soon we should start seeing the logging information I defined to be printed. It should start appearing. Yeah, there you go, as the training starts taking place. So we see, as we'd hope, the loss function, so the loss is on certain batches is decreasing as time goes on. First epoch was done, and we see the test accuracy is around 92%. And we'll just let it train a bit. This should be really quite quick. It's a very small model. In fact, I would imagine we're not getting much benefit from the GPU here for such a small model. The benefits relative to CPU are going to be much more dramatic when we start looking at larger models and with certain operations and larger data sets. And we see here, it's finished running. After 3 epochs, we were able to hit 94% test accuracy. And you should perhaps maybe be able to do slightly better on such a model on MNIST. And so that just about wraps up this this introduction to NumPy and PyTorch. I hope you find this useful and a good starting point to build on for the rest of the course. I'll emphasize again, there are many more features in PyTorch that you will be using in this course, and we'll be introducing them bit by bit. And don't be afraid to get familiar with the documentation, and just to get a sense for what kind of features are in the library. And unless we explicitly tell you to implement something from scratch, there's a good chance that there's something very useful to achieve your goal has already been defined in the library. Yeah, so just get some sense of what is out there by looking at the documentation. Right, I hope you found this useful. I'll wrap up here now, and I guess we'll see you in the labs with any questions you might have.